Okay, reinforcing bars. We need to talk about this. The steel that goes into concrete comes in bars, and they have different sizes, number 3 through 18. Okay, in this class, we'll use these numbers, but when you buy them, number 3 will say something like 11 on it. I have a table that shows the numbers on the next slide. We'll talk about that. But these bar sizes, we'll use these numbers 3 through 18. They're approximately the diameter in eighths of inches. Okay, so a number 4 is roughly 4/8 inch or ½ inch in diameter. And it's not the actual diameter because these bars, they have ribs on them like this. And so it's the average diameter, not the actual outside diameter. Um, and it's based on the weight per foot, and then they calculate what the equivalent diameter will be. Always look up the area of the bar. Don't compute it as a circle for a couple of reasons. A, is just more convenient, but B, it's approximately the diameter size. When you get above a number 9, the diameter does not equal the number divided by 8. I'll talk about that in a little bit. Okay, so first thing I want to talk about is the designation. So number 3 bar is roughly 3/8 inch. But on the bar, it will actually say 10 because 10 millimeters is roughly 3/8 inch. Now, why do they do this? Okay, so a while back when the US was considering converting to metric, passed a law that all rebar would have to have the metric size. And what we were going to do is we're going to go US to what's called soft metric. And what that was, it was still a number 3 bar, 3/8 inch diameter, but you would find the closest metric measurement and call it that. And then eventually we would go to the metric bars, and actually the metric bars make more sense. We won't talk about them here. We don't use those, but the metric bars are sized by areas. They're very intelligent, really well done. And so what you had to do when you converted to soft metric, all they had to do was take the number 3 off of the bar and put 10 on the bar, because then it would indicate it was 10 millimeters roughly, but it was really 3/8 inch. But you know, these are molds to make these bars, so it's expensive to make this change. You have to throw away all the old molds, make new molds that said 10 on it. Well, we get a few years into this conversion to metric, and then we give up. And say, oh, we're going back to English units. Well, the rebar companies are saying, we're not going to make another set of molds. We just changed all our molds over. So we're keeping the metric numbers on them. You're just going to have to remember that 10 actually means a number 3. So here we go. These are, so first of all, this is from your book. You can see like, I've got it tagged because I use this table a lot. So these are the numbers you would use in your drawing, number 3, number 4, but these are the actual markings on the bar, 10, 13, 16, and those aren't actually metric bars. There are metric bars. Maybe another day we'll talk about it, or maybe in class, I'll talk about the metric bars. And here are the diameters. And so you can see that it kind of works. See, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8, but here, 9/8 is 1.125 square inches. And 10/8 is what? 10 over 8 should be 1.25. So these are all not the right diameters if you take the number and divide it by 8. So what is that? Okay. Before we had round bars, we had square bars. And so 1 inch square was this. Let me take the square root of 1.27. So 1.27 square inches. Here we go. 1.27. Oh, that's 1 1/8, etc. These are equivalent square bars. And so what happened is that when we changed from square bars to these newfangled circular bars, people back then complained. They say, what? We have to do pi r squared. Square area is just height squared. You guys are making our life so hard. So we kept from number 9 and up, they're actually equivalent square bars, so people would stop complaining. I actually have a piece of a square rebar cut from a bridge that sank. Yeah, it's kind of weird. So this is why you can't take the diameter to calculate the area. From number 9 and on, it doesn't work. Okay, so this table is super handy to use in the back of your book. Okay, so here are what the bar notations look like. And so you can look at the bar. This thing here tells you what mil. See, here's that weird number 11. So number 11, oh, that actually is a 11 bar. So this is old. Now this number, that 11 bar, that would actually say 36 now. Okay, and here you can see the deformed patterns. Yeah, so this is a little slide on how to read rebar markings. If you're in the field, it used to be easy, like in the lab, I could pick a bar up, say, oh, is it a 3 or a 4? You would look at the number, but now I don't have these numbers memorized, 10, 13, 16, so for me, it's useless. I can't tell what size a bar is by looking at the marker. Okay, so let's look at the stress strain curve for steel. Use grade 40 through 60 in our class. We don't use these too much. Those are high strength steels. And this front part here is blown up over here. And what's interesting, unlike concrete, no matter how strong the steel is, it has the same slope. The E is constant, and it's 29 million psi. So the E of concrete changes with the strength, but the E of steel does not. E is always 29 million for steel. Okay, so I want to talk about pre-stressing steel. So here we go. These are like super high strength, 270 KSI, 250 KSI, compared to what we're using in this class. This is actually kind of a big deal in pre-stressed concrete. You'll talk more about that if you take the pre-stressed concrete class on why this is important. Until we developed high-strength steel, pre-stressed concrete was not really practical. Okay, and if you have pre-stressed concrete, it's kind of an interesting thing. So you get some steel, okay, and then I don't know, like this, and you stretch it. Obviously, it wouldn't look something like that, but you stretch it to a certain stress. Okay, so F initial, and then later, so it's like the opposite of creep. The deflection is not changing. So creep, the deflection changes with constant stress. Here, the deflection is constant, but the stress is reducing over time. The stress goes down and down and down over time, and it's relaxing. It's called relaxation. And here's a formula on how to do it. Okay. And that's all you need to know for materials for this class. So next time we'll start our first lecture about flexure or moment, bending in concrete.